all should be able to get in there. Just give it one more second. I'm live now here. Can you see that, guys? Yeah. Okay, brilliant. Now what I'm going to do is I'm just going to mute myself here on Teams, and I'm just going to check my mic on this other thing here on YouTube just to see whether that's working. Okay, I should be still able to hear you guys. I should still be able to hear you guys. Okay, guys, I'm now on. I can actually see that three of you have joined. I'm just waiting on one more. I suppose my question to you now is, can you hear me through YouTube? You can hear me through YouTube. Brilliant. Okay, that's excellent. Okay, so well then maybe what I should do is I should get going. Yeah. Okay, and let's just kick into this. Yeah. I have a tendency to write from the right-hand side of the page across to the left-hand side of the page for some reason. So maybe I'll just keep going in that direction. Yeah. So up to this particular stage, what we've looked at, I think last week was we looked at simple linear regression. Okay, so we looked at simple. The last time we met just before the break, simple linear regression. Okay. And basically what that was we had a single dependent variable. Okay, single dependent variable, and we had a single independent variable. Okay, and we recognized that there was a population. Okay, so we're looking at the relationship between the independent variable and the dependent variable, and what we had was we had our independent variable along here, we have our dependent variable along here. And inside the population itself, what we had was we had observations real observations within the population. And within the population, I suppose we could construct a line of best fit. Okay. So let's just say here's the line of best fit in the population. Okay. And that line of best fit in the population, so from a population perspective, okay, the line of best fit is y is equal to beta 0 plus beta 1 times x, the independent variable. And the job we wanted to do was to try to estimate these beta 0s and these beta 1s. In that case, we basically had the relationship between them. But what we do recognize is that we never have access to the full population. Okay. Let me just focus this in a little bit more here, guys, just to see will that focus a bit better. Just 1 second there. Yeah, let that focus. There we go. I think that's a bit sharper now. So what we recognize is that we never have what's that? Okay, I'm just going to mute that there now. Yeah, okay, brilliant. What we recognize is that we never have the full population. And what we do is we randomly sample from it. So let's say we sampled here. Let's say here, here. And let's say for argument's sake that we sampled here. Okay. And based off that sample, what we could do is we could put in a line of best fit. We could estimate a line of best fit. So in this case, maybe the line of best fit looks like that. So from the sample perspective, okay, the line of best fit was y bar, the estimated value, is equal to sum b0 plus b1 times x observations. Let's just keep in mind that even in the population, that in general, not all of the points are on the line. So in the population, that there's some sort of error in the population, we'll call that epsilon. And then in the sample, not all the points will be on the line in the sample case, so that there's some sort of error as well there. We're not interested in trying to understand that error at this stage, okay? Other than the least squares approach is going to minimize that error for us and find the line of best fit that goes through the data set, okay? And last week, or the week before we broke up, the last class that we had, we came up and we proved a way of actually estimating these beta 0s and beta 1s by calculating these b 0s and b 1s. Okay, so effectively that's what we did. That's what we did last week. Yeah. What we want to do now this evening is we want to extend that without proof. Okay, it's a little bit more. It's the same technique that we had last week. It's just that we're throwing in another independent variable. So I mean, if you want to try to construct the formulas yourself, you're more than welcome to go off and try to construct them. There's a bit of work involved in it, but you just need it to be that tenacity, yeah, just to keep going with it, yeah, and you will get there. But the formulas are a little bit crazy looking. Actually, I'm going to present two different ways of actually solving this evening. I'll give you the first way, which is using this, let's say, the sums of squares approach, yeah. So what we're going to look at now this evening is our multiple linear regression model, okay, regression. And what we effectively have is we still have a single dependent variable, okay, variable, but we have two independent variables, okay. So, I mean, that might be something like maybe we're trying to predict the Isaac benchmark index. So maybe we're trying to predict the Isaac, and we're trying to predict the Isaac by observing, let's say, Ryanair stock, and also by observing, let's say, just say for argument's sake, Dragon Oil stock, if that makes sense, yeah. And what we're really trying to do is we're trying to identify, let's say, what this B1 is and the B2 is here, and what the B0 is, to give us a linear equation, if that makes sense, yeah. Okay. So the question is, how the hell do we calculate these things? How do we calculate B0, B1, and B2 when we know what Y is, okay? We know what X1 is, and we know what X2 is. Last week, as I said, we presented formulas for calculating B0 and B1. Actually, B1, if I'm not mistaken, let me just think here. Yeah, so B1 last week was n times the sum of the xy's minus the sum of the x's times the sum of the y's divided by n times the sum of the x squareds minus the sum of the x's all to be squared. That was our B1 coefficient, okay? And B0 was equal to the average of the y's minus the B1 times the average of the x's. So all we had to do is when we had all the observations, the y observations and their associated x observations, we basically calculated the squares of the x's, the cross product of the x's and the y's, and it was pretty straightforward to calculate what B1 and B0 is. It's a little bit more involved, and I suppose there's probably a simpler way to do it, but I think the expectation is that we use a different approach. If I was to give you formulas, I'll give you the one way that we could do it first of all, okay? So let's say the formulae, okay, for calculating B0, B1, and B2, okay, that should be and, okay, not plus, okay. From a correlation perspective, B1 is simply equal to the correlation, okay, between the first independent variable and the y, okay, minus the correlation between the second independent variable and the y, times the correlation between the two independent variables, okay, 1 and 2, divided by 1 minus the square of the correlation between 1 and 2. So that's what B1 is. So it's actually easy enough to calculate, okay, from a correlation perspective. I don't know why I didn't actually just use this approach and actually provide them formulas in the formula book. What I did was I actually went off and we actually, the way we proved it last week, okay, the way we proved it last week in relation to estimating B0 and B1, I did that approach for the two independent variable cases and ended up with they're massive formulas, yeah. But you can probably understand actually if the correlation calculation, the correlation formula, let's say, or correlation, let's say, between an x and a y is equal to n times the sum of the x, y's minus the sum of the x's times the sum of the y's divided by n times the sum of the x squareds minus the sum of the x's all to be squared times n times the sum of the y squareds minus the sum of the y's all to be squared, and it's actually the square root of that, okay? So you can see we've done that. Now I know that's at an angle there, guys, yeah, okay? But really what I'm saying is that we did this last semester, how to calculate the correlation between two variables, yeah? An independent and dependent variable. So you can probably see that this is how you calculate the correlation between two variables, yeah? We could take that and plug it in here, but this time the variables is the forced independent variable with the y, the dependent variable. We could take that and plug it in here, take that and plug it in here, and then take that again and square it here, which I think you can understand is that gives us a massive formula to deal with, okay? So let's actually, so I'm actually just going to stick with this approach because it's probably a little bit better. And what we'll do is we'll just run all the correlations, yeah, and we'll calculate B1 and B2. B2, rather than using the formulas that's in the book that I've provided, because them formulas, it's very hard to actually figure out what's actually going on under the hood there, yeah. Okay, B2, the coefficient here, okay, is equal to the correlation between the second independent variable and the y, minus the correlation between the force independent variable and the y times the correlation between the two independent variables, divided by 1 minus the square of the correlation between the two independent variables. Okay, and then B0 is simply equal to the average of the y's minus B1 times the average of the x's minus B2 times, the average of the force independent variable times minus B2 times the average of the second independent variable. Okay? So equipped with this, and this, okay, we can effectively figure out this particular model. Yeah. So that's just really an overview there. Yeah, let's just go into a little bit more detail if that's okay. I'll just unmute this here. So I'm just unmuting Teams there just in case there's any questions. So just so that I can actually hear you guys. Is everybody okay so far? Oh, you probably have to flick back onto Teams. Yeah. Okay. So maybe just ignore that then. Yeah. I'll just come back here now. Yeah. Okay. So let's just have a look at this again. Okay. So what we have is, once again, we have a population. This time we've got two independent variables. So what we have is we have a population. We have our force independent variable. Let's say independent 1. Okay. I'll just put our dependent variable up here. So we have dependent variable. And then what we have is we have our second independent variable 2. Okay. And what we have now is, so we've got 3 observations. Yeah, we've got 2 independent observations and we've got dependent observations. So basically what we end up with is we end up with points. We end up with points in tree space, okay? Somewhere in tree space. And what our job is to try to find, this time, a plane, okay, of best fit that goes through those particular points. From a population perspective, okay, there is a plane of best fit, and the plane looks like y is equal to beta 0 plus beta 1 times the force independent variable plus beta 2 times the second independent variable. And in general, the line, this particular plane, not all the points are going to be on the plane, so there's actually going to be some error, and let's call that epsilon. So this is what we're trying to understand. And what we're going to do is we're going to sample. Okay, so we're going to sample from that particular surface, yeah, or that particular let's say tree space. We're going to sample, and what we're going to try to build is an estimate of the y, and the estimate of the y is going to give us, we're going to have a b0 plus a b1 times the force independent variable plus a b2 times the second independent variable, and we recognize that there's going to be some error in the model. So this is really what we're trying to do. And a moment ago, you can actually see that this form here, this is the general form here, okay? It's what I was talking about here. In this case, yes, we're going to estimate what the Isaac values are by looking at Ryanair values and Dragon Isle values, or Dragon Isle observations and Ryanair observations. But which we have, don't forget, we have the Isaac values, we have the Ryanair values, we have the Dragon Isle values. All that's missing for us is to calculate what B0, B1, and B2 is. And the way we're going to do it is we're going to do it by, let's just do it using correlations rather than any other approach. Okay. Is everybody okay there? You can probably, in the chat window in YouTube, you can probably just indicate with a Y if you're fine so far, if you understand and you're keeping up with what the goal is. The goal is basically to extend the simple linear model into a situation where we've got more than one independent variable. Is everybody okay there? Okay. I'll just type something here into the chat window here on YouTube. Okay. Are you guys all okay with this so far? Okay. So Connor, brilliant. Yeah, great. Yitzis, brilliant. Mima, how are you? Okay. Mima, are you okay? If you just maybe type a Y into the live chat. Mark, are you okay? Okay. Look, I'll just continue. You'll be able to replay this maybe later on. Yeah. Okay. So let's just take some observations, just as an example. Okay. Let's say, for argument's sake, that we have two independent variables. I'm just going to build a table here. Okay. I'll keep it small. Okay. So we have our first independent variable, Ryanair, and let's say the observations are 2, 4, 6, let's say 7. Let's keep this small. Okay. Let's say we have a second independent variable. Let's say the observations are 4, 1, let's say 5 and 3. And let's say we have a dependent variable y, okay? And the observations are, let's say for argument's sake, that the observations are, let's say 10, 8, 12, and let's say for argument's sake, let's say that they're 9, okay? And what we want to do is we want to calculate B0, B1, and B2, yeah, okay? In relation to this particular model. And the way we're going to do it is we're going to use our correlations, okay? So just keep in mind, once again, is, let me just go back here, okay? So the alternative formula perspective, B1 is just a set of correlations that we need to calculate. The B2 is also a set of correlations, and B0 is just going to use the two previous coefficients that we've identified, along with the average of the dependent variable and the two averages associated with the two independent variables. So I think what we probably should do is let's calculate the correlation between the first independent variable and the dependent variable. Okay, so let's keep the formula in mind. So our formula is that the correlation in general is equal to n times the sum of the xy's minus the sum of the x's times the sum of the y's divided by n times the sum of the x squareds minus the sum of the x's all to be squared times n times the sum of the y squareds minus the sum of the y's all to be squared. And it's the square root of that guy there, okay? So if we so we're not going to have to do y twice, yeah, okay? So if we calculate, first of all, the correlation between, let's say, so we want to calculate the correlation between, let's say, x1 and y, okay? Well, let's just assume that x1 is the x variable and y is the y variable. So what we need to calculate is we need to calculate the cross product between x1 and y, okay? We need to calculate the squares of x1, so x1 squared, okay? We need to calculate the squares of y, so we need to calculate our y squareds, okay? And that's really all that we require to calculate the correlation between x1 and y. So let's do that. So the cross products is 2 times 10 gives us 20. 4 times 8 is 32. 6 times 12 is, what's 6 times 12? That's 72. We have 7 times 9 is 63. Okay. So they're basically the cross products. Okay. Then what we need to calculate is x1 squared. So x1 is 2, so its squared is 4. When it's 4, it's 16. When it's 6, it's 36. When it's 7, it's 49. And then finally, the y squared values. Well, y is 10. The square is 100. When it's 8, it's 64. When it's 12, it's 144. And when it's 9, it's 81. Okay. So we can basically now calculate the correlation. So or in this case, or between x1 and y is equal to n, the number of observations, the number of, I suppose, let's say triples that we have. So we've got 1, 2, 3, 4. So it's 4 times the sum of the xy's. Okay. So the sum of the xy's is the cross product term. So we need to sum these up here. So what we've got, we have 20, we have 50, excuse me, we have 120, we have 180, we have 183, we have 187 here is the sum of the cross products. That's 187, okay? Minus the sum of the x's. Well, the sum of the x's is 2, 6, 12, 19. So it's 19 times the sum of the y's is 10, 18, 30. We have 39, okay? And that needs to be divided by, well, that's what I say, that's 39, and that's 19 here. And that all needs to be divided by, so we've effectively got 1, 2, 3, I think it's about 3 correlations to calculate here, guys, yeah, okay? Sorry, okay, Mark's Wi-Fi isn't great there, okay? So then what we have is the denominator here, it's n, it's 4 times the sum of the x squared terms, okay, for the first variable. So the x squared terms are here, it's 4 and 16, that gives us 20, that gives us 56, that gives us 96, that gives us 105 here, okay? So it's times 105 minus the sum of the x's to be squared, which is 19 to be squared, okay? And then that's times n, which is 4 times the sum of the y squared terms. Okay, well, the y squared terms are here. That's 100, 160, 200. 260, 300, 385, if I'm not mistaken. Yeah, okay, times 385 minus the sum of the y's all to be squared, which is 39 to be squared, okay? And then don't forget, it's the square root of that guy there. So if I just do the numerator and then the denominator, so just on the calculator here, I have, you probably can't see that there. Maybe, is that a bit better here? It's probably just not picking it up yet. It's the lights shining down here, but anyway, it's 4 times 187 minus 19 times 39. That gives us a value of 7, okay? So the numerator is 7. The denominator here is, let's say, I'll just do what's inside here. So it's 4 times 105 minus 19 to be squared gives us a value of 59. So it's 59. It's 4 times 385 minus 39 to be squared gives us a value of 19. And it's the square root of that. So the correlation between the first independent variable and the y is effectively equal to 7 divided by the square root of 59 times 19, which gives us a value of 0.21. Okay, so there's a small correlation between those two. Okay, so that's the first one done. So that's the first independent variable times the y. Let's do the second independent variable times the y. Okay, let's see how we get on there. So let's have a look at that. So the second independent variable times the y, I need to calculate the cross product. So I need to calculate x2 times y. Okay. So let's do that. So it's 4 times 10 gives me 40. 1 times 8 gives me 8. 5 times 12 gives me 60. And 3 9s gives me 27. The sum of those there is 127. And the 8 gives me 135 there. Okay. And we need the sum of the x2 term, which is 4 and 1 is 5, 10, 13. So now we have that. We need the sum of the y's, which we've already calculated. We need to calculate the square of the x2 term. So we need to calculate x2 squared. Okay. So it's going to be 4 squared is 16, 1 squared is 1, 5 squared is 25, 3 squared is 9. And the sum of them there gives us, well, what do we have? We have the 1 and the 9 gives us the 10. That gives us 35, 45. That gives us 51, if I'm not mistaken. Okay? And then we need the sum of the x2 terms, which is 13. We've already got that. We've got the y squared terms and we've got the y's. So we can actually calculate the correlation now between the two of them. So let me maybe just fold this page over. Okay, let me just calculate that correlation. I think this is probably the easier way to do it. It's a lot of work, I do accept. So we want to calculate now the correlation between the second independent variable and the y, okay? And that's equal to n, which is 4, times the sum of the cross products between the second independent variable and the y, which is 145, minus the sum of the second independent variable, which is 13, times the sum of the y's, which is 39. Okay? And that needs to be divided by n, which is 4, times the sum of the square of the second independent variable, which is 51, minus the sum of the second independent variable, which is 13 to be squared, times 4, times the sum of the y squared terms is 385, okay, minus the sum of the y's to be squared, which is times 49. Okay. There's actually a little bit of redundancy here, so we probably should have done everything independently, yeah, because you can see that this term has appeared in a couple of times, yeah. But anyway, what we effectively have, I'll do the numerator first. It's 4 times 135 minus 13 times 39, which gives us a value of 33, which needs to be divided by, and I'll just do each one of these separately. It's 4 times 51 minus 13 squared. Okay, that gives us a value of 35, and we've already calculated this term here. If I'm not mistaken, it is 19. Okay, so that's times 19, and it's the square root of that we need to get. So in this case here, we end up with 33 divided by the square root of 35 times 19, and that gives us a value of that doesn't make any sense there now. Okay, so it's 33 divided by the square root of 35 times 19, which gives us a value of 1.27. So we made a mistake somewhere. Whoa, so where the hell did we make the mistake? Yeah, so let's just think here again. That's good. That's 19. So let me just check this here. So 4 times 385, that's good, minus 39 squared. That gives us a value of 19. That's good. Okay. 4 times 51 minus 13 squared. That gives us a value of 35. That's good. 4 times 135 minus, so 135 minus 13 times 39. That gives us a value of 33. And well, so there's an error here, guys, somewhere. So let me just actually just root through this, yeah, and try to get that out. Probably should have taken a little bit more time here. So we have the x2 term. Let's just sum it up. 4, 5, 10, 13. That's good. Okay. We have the sum of the y's is 39, 10, 18. And that's 30, 39. That's good. Okay. The cross products between the x2 terms and the y, 4 times 10 is 40. 1 times 8 is 8. 5 times 12 is 60. 3 nines is 27. The summation of this is 48. That's 108. 108 and 27 is 135. That seems to be good. We need the x squared term. 4 squared is 16. 1 squared is 1. 5 squared is 25. 3 squared is 9. That gives us what have we got here? That gives us 30. Excuse me. That gives us 10. That gives us 35. 45, 51. That seems to be good. Just the y squareds. 10, that's 100. That's 8, 64, 144. 9 nines is 81. That's 164, 168, 200, 300, 368, 369. Is that right? Sorry, guys. Let me just do that again here. Yeah. It's 100 plus 64 plus 144 plus 81 gives us a value of 389. Okay, that's important there. So that should be, this here should be 389. Okay, which changes things, I think, a little bit. It's 4 times 389 minus 39 squared gives us a value of 35. So that should be 35 here. So it's 33 divided by the square root of 35 times 35, which now gives us a value of 0.94. So that's 0.94. Just going back over here, that here should be also 389. So now what we have is 4 times 389 minus 39 squared gives us a value of 35. So that also should be 35. So that should be 35, which just changes the correlation coefficient. So a little bit of a problem there in the summations. You have to be really careful here when you're summing this stuff up. Yeah. Okay. So now we have 7 divided by the square root of 59 times 35, and it gives us a correlation of not 0.21, 0.15. Okay. Just moving ahead now. So you can see there's a lot of work involved in this. Like this in the exam, like I think this is probably worth about 25% in the exam, this particular calculation. Yeah. So we've calculated the correlations between the two independent variables and the dependent variable. So effectively what we now have is we've calculated this correlation here, and we've calculated that correlation there. Okay. So we've also got that, and we've got that. So the only thing now that we're missing is the correlation between the two independent variables. So the third correlation now to calculate is the correlation between x1 and x2. Okay. So in that case, let me just maybe just get a little bit more space here. Hopefully this will work. Okay. So in that case here, so we've already done all the x1 terms. So we've done the I suppose we've done the x2 terms as well. So we actually should be fine. The only thing that we haven't done is the cross product of the x1s with the x2s. So x1 times x2 is 2 times 4 gives us 8. 4 times 1 is 4. 6 times 5 is 30. 7 3s is 21. What does that give us? That gives us 8. That gives us 8, 12, 13. That gives us 63, if I'm not mistaken. Hopefully somebody's sanity checking me here as well. Is it 51 and not 105? Is it 51? 51 and not 105. This one here, is that right? I think that's actually good, yeah. Gitas, you've asked, is it 51 and not 105? Yeah, I'm just wondering which 105 are we talking about? This 105 here. That's the sum of the x1 squared terms, yeah. Could be. Never mind. Okay, right. That's grand. Yeah, I think we've sorted out the problem here. Yeah, but maybe somebody can sanity check this then later for me. But I think we're effectively good to go now. So now the correlation is n, which is 4 times the sum of the xy's, which is the cross product between the two independent variables, which is 63, minus the sum of the first independent variable, which is 19, times, this time y is going to be the second independent variable, which is times 13, which needs to be divided by n, which is 4, times the sum of the squares of the first independent variable, which is 105, minus the square of the sum of the first independent, which is 19 to be squared, times 4 times the sum of the square of the second independent variable, which is times 51, minus the sum of the second independent variable to be squared, which is 13 to be squared. And once again, it's the square root of that. So I'll just do the numerator again first. So we end up with 4 times 63 minus 19 times 13 gives us a value of 5, which needs to be divided by this value here. We already know what that is. That is 59. Maybe just sanity check it. It's 4 times 105 minus 19 squared, which gives us a value of 59. And this term here is 4 times 51 minus 13 to be squared, which gives us a value of 35, and it's the square root of that. So this gives us 5 divided by the square root of 59 times 35, which gives us a value of 0.11. Okay? So we now have our three correlations. Let's just write them down. So the correlation between the force independent variable and the force and the dependent variable is equal to 0.15. Okay, that's effectively R1y. Okay, then we have the correlation between the second independent variable and the y. We just calculate that there to be 0.94. That's effectively R2y. Okay, and then finally we have the correlation between the two independent variables. Okay, which is 0.11, and that's effectively R12. Okay, so now we can build our model. So our B1 term, so the first coefficient B1 is equal to the correlation between the force independent variable and the dependent variable, which is 0.15 minus the correlation between the second independent variable and the dependent variable, okay, which is 0.94 times the cross product correlation 0.11 divided by 1 minus the cross product 1 squared, 0.11 squared, okay, which gives us a value of, in this case, the numerator is 0.15 minus 0.94 times 0.11 gives us a value of 0.064. Let's just say, actually, let me just keep it accurate, yeah? Divide that by, then we have 1 minus 0.11 to be squared. Okay, and this gives us in total, we have 0.047, 0.047 to 3 decimal places. Okay. The second coefficient, the B2, is the correlation between the second independent variable and the dependent variable. So it's 0.94 minus the correlation between the force independent variable and the dependent variable, which is 0.15, times the cross product one, which is correlation between 1 and 2, which is 0.11. So you can just see we're actually just flipping these two things around here, divided by 1 minus 0.11 to be squared. And when I do that all in one go there, I get 0.94 minus 0.15 times 0.11, and that needs to be divided by 1 minus 0.11 to be squared. Okay, so when we do that there, we get a value of 0.935. So 0.935. Okay, and then finally the B0 term is equal to, well, it's equal to the average of the y's. Okay, so let's just get back to our table there. So we know what the sum of the y's is 39. So 39 divided by 4 gives us a value of 9.75. So it's 9.75 minus B1, which is 0.047 times the average. We'll just get that back in here, times the average of the force independent variable. Now the sum of the force independent variable is 19, so 19 divided by 4 is going to give us a value of 4.75 minus, let's get that back in, minus B2 times the average of the second independent variable. So it's minus B2, which is 0.935 times the average of the second independent variable, which is 13 divided by 4, which gives us a value of 3.25. Okay, so B0 is equal to 9.75 minus 0.047 times 4.75 minus 0.935 times 3.25 gives us a value of 6.488. So 6.488 is what we've ended up with there. Okay, so effectively the model now is, okay, so I know that, look, come here guys, I know there's a lot of work here, but let's just actually now just get the model. So we have just calculated our B1 our B2, and we've calculated the constant term, yeah, where the plane intersects, I suppose, let's say the dependent variable plane, yeah. So now the model actually is that we now have that our y's, where's that gone to? Here's my marker here. Our y's, our estimated y's are equal to 6.488, okay, plus 0.047 times the first independent variable plus 0.935 times the second independent variable. That's effectively the regression model now. That's how we're going to estimate. We can estimate these y values from. So there's the model that we've effectively built. Look, there's a lot of work there, but I think it's a more intuitive actually going through the correlation values. We'll sanity check this back in Teams in a moment. I'll share my desktop and we'll actually just run it in SPSS and see how we get on. Okay, if that makes sense. But that's basically the calculation, guys. That's how you calculate it in the two independent variable cases. Okay? Is everybody good with that? Bit of work involved there. You're going to obviously have to drill that down. You're definitely going to see one of those in the alternative assessment, okay, where you're given some independent variables, two independent variables and a dependent variable, and you're going to have to build a regression model effectively like this. Yeah, okay, if that makes sense. Okay. Another question that we might ask ourselves, yeah. Back now to Teams, yeah. So I'm going to turn away from YouTube for the moment. I'm just going to go back to Teams and let's just have a little bit of a chat in Teams for a moment, if that's okay. Right? Hi guys, can you hear me again? Okay. Where you look, tell the truth. Where you having a nap there? Where you? Yeah. Look, you can see that's probably a bit of work involved. And look, in the real world, you're not going to be doing any of this by hand. You're obviously going to be doing it in SPSS. So let's just see, because we can see in YouTube what the model actually looks like. Let's just sanity check this, and fingers crossed that I didn't make too many hand calculation mistakes. Yeah. So what I'm going to just do here is I'm just going to share. My desktop. I'm just sharing my desktop here now, guys. And what we have now is I just got SPSS here. I'm just getting a new data set here. Save changes. No. So here's my new data set. Can everybody see my desktop okay? Okay. So all I'm just going to do is I'm just going to take that. Yeah, okay, good. So I'm just going to create my three variables. Yeah, so let's just call this y, and let's call this x1 and x2, and they're scaled variables. So they're scaled variables, scaled, and let's just put in our data. Let's just actually build them up. So my y observations were 10, 8, 12, and 9. Okay. My first independent variable observations were 2, 4, 2, 4, yeah, that's right. 6, 7. And my second independent variables were 4, 1, 5, and 3. Okay. So what we want to do is we want to build the regression model. I'll just close down the previous output. That was actually supposed to be in there last time, which just happens as well to be the regression model as well. Okay, so I'm just going to go to analyze. I'm going to go to regression. I'm going to call for linear regression. My dependent variable is y. Okay, when you're doing this, obviously myself, your project, your dependent variables are going to have real names like stock names and chosen. And my two independent variables are x1 and x2. Statistics, I'm just going to leave everything the way it is. I'll go from collinearity diagnostics as well to descriptives, and double Watson as well, residuals. There's preconditions associated with these regression models. We might as well just check them out here as well. And it will save. I'm going to save the unstandardized residuals as well. Okay. That's just like a separate residual. Actually, let's standardize them around 0. Yeah, so we'll standardize them. Just save the residuals. That's the error in the model we're just saving out. So it's really going to throw in my x1s and my x2s into the model and estimate this new y value. So let's actually save that. Continue. Actually, let me see that. I don't want that equal variance matrix. So let's that. That's all good. And there we go. Okay. So effectively, you don't really need to do anything over here. I'm just running some extra stuff. Let me just do that again. By default, we get the estimates. We get the model fit. I'm asking for descriptives and also collinearity diagnostics. And also in relation to residuals, looking at outliers and things like that. So I'm looking at double Watson and I'm also saving the residuals, not standardized residuals. That's just where it throws in the x1 and the x2 into the model that it's estimated and gives you what the estimated y value is. And then standardizing them just means that we take away the mean and divide by the standard deviation. So basically, that's what we're saying. So I hit continue here, and I'm going to hit OK. And what we get here is we just get a lot of output. So it's telling us just the descriptive statistics. The y value here, the dependent variable has an average of 9.75, the standard deviation of 3.70. Effectively, this is what we're trying to estimate and understand. We're trying to understand as much of the variation in the dependent variable as possible, by considering the variation in the x1 and the x2s. So let's just go down to correlations and see if there's correlations between these variables. We had identified our correlations a moment ago. What did we say? The correlation between x1 and y, we estimate as 0.15. It's saying it's 0.154, so we were good there. The correlation between the y and the x2 is 0.943, and we got 0.94, so that's good. And then the correlation between the x1 and the x2 is 0.11, which is exactly what we got there, 0.11. So that's actually good too. So we know that we did pretty well there, so no problems. Scrolling down here, let's just go down to the coefficients here. And you can actually see here's the b values, here's the estimates here of the coefficients that we just got. And constant term 6.518. That's where have I gone to here? Well, I got 6.488. Pretty close there we are. Okay, bit of rounding error. The x1 coefficient is 0.039. Well, there you go. Look, it's 0.4 there. We got, don't forget, a bit of rounding error there as well. We got, where's that one? We got 0.047, so pretty close. And then we have here the coefficient of the second independent variable is 0.937, and we got 0.935. So I think we're pretty close here. All that's actually after sneaking in is some rounding error, if that makes sense. So this is good. So the hand calculation actually did the job for us here. Is everybody okay with that? Just scrolling back up here now. A question that we might ask ourselves is something like this, is that, okay, if we're trying to understand the variation in the dependent variable, and we're trying to account for that variation by controlling the x1 and the x2 variable effectively. So what the model summary basically tells us here is, first of all, the correlation. This is a multiple correlation. The correlation between the two independent variables and the dependent variable. So how well correlated are these two things with the dependent variable overall? And it's 0.944, which is a very, very strong correlation. And then we have R squared here. R squared is the proportion or the percentage of the One thing to keep in mind when we're building a multiple regression model, the more variables that we throw in, the more independent variables that we throw into the model, the R-squared term just naturally increases. So it's really important that when you're building these models that you're based off some sort of theory, okay? And you don't just keep throwing in independent variables for the sake of it, because eventually you're going to just keep putting in independent variables and that R-squared is going to increase. A more appropriate measure is this adjusted R-squared that takes into consideration how many independent variables are in the mix. So a more appropriate measure is 0.67. 67% of the variation in our dependent variable we account for. That's a big difference between what we have here with the R-squared term. Yeah? So that's good. The other question that we might ask ourselves is, can we trust the model itself? Is this R-squared term, is it, let's say, statistically significant based off our observations? The ANOVA here, like in our typical ANOVA, the default position is the model is crap. The alternative position, so the null position of the model is crap. The alternative position is that the model is good. It's statistically significant. Yeah? Now we can see the significance here is 0.329. And once again, we're failing to reject the null. The p isn't low enough here, so we're failing to reject the null. So actually, to be honest with you, even though we can account for 67% of the variation in the dependent variable, it's not statistically significant what this is saying to us here. Another thing just to keep an eye on is the assumptions associated with a regression model. Okay? They're called the Gauss-Markov assumptions, and there's 8 of them. Starting off, I suppose it's important that the variables themselves, the independent variables and the dependent variables, have a particular scale of measure associated with them. So the dependent variable needs to be continuous. The independent variables need to be continuous as well, or dichotomous. Yeah? Okay? In other words, take on one of two measures. Yeah? So R3 independent variables are all continuous. R2 independent variables are continuous, and some independent variables. So we're okay here. We have to make sure that there is a linear relationship between each independent variable in isolation and the dependent variable. What we could do is we could look at the scatter plots to see whether they are linearly independent of each other. Just this doesn't tell us it definitively, but it's a way to look at it. So we could scatter plot y and x1. We can have a look at that. So we can actually see here. 24 observations. Bad for example. At some stage, here's a line. So look, the thing that we want to really see is we want to see the points all scattered around the line of best fit. We don't want to see any curvature, things like that in scattering. Yeah? So when we use a scatter plot to actually observe linearity, that would be a good way to observe linearity. Another thing is that the independent variables themselves shouldn't be linearly dependent on each other. Yeah? That they should not have a linear relationship with each other. And one way we can do that is with collinearity statistics, yeah, and the tolerance values. Any value above. So this is basically regressing, yeah, the independent variables on each other. Yeah? It just happens that we have 2 of them. So we're actually going to get the same values out here. But a tolerance value above 0.1 is good. In this case, we've got 0.988, which is very good. So above 0.1 or above 0.2 is a good value for us, which means that there's no evidence of a linear relationship between the independent variables. That's really good for us. Something else just to keep an eye on is just in relation to the residuals. Okay? So here's our residuals here. There's not many residuals in the sequence. There's only 4. Yeah? They need to be normally distributed. Yeah? The error in the model needs to be normally distributed effectively. Yeah? So we could actually test to see whether they're normally distributed. We could do a histogram of the air case with only 4 observations. We're not really going to get into it here. So let's just take our residuals from the standardized ones. Let's just put them in. We want to see a normal curve. Now we can see that's a constant curve here, yeah, but that's a bit of a problem here. So our residuals should be normal, yeah. And in which case, look at 4 observations here, we're not going to get that. look, I only went here now just to show you, yeah, is that what we actually effectively have done here is just this was just a sanity check, our hand calculations. So our hand calculations actually are all good there. That makes sense. Okay. Any questions, guys? Connor, any questions? Yeah, yeah, just get in. Yeah, just get in there. I have got a video up in relation to how to build a multiple regression model in SPSS that goes through things a little bit slower, yeah? So maybe you can have a look at that, because that's what you're going to have to do for your project, yeah? Okay. And Mima, look, come here, I do accept that. Look, come here, this is doing a lot, and, obviously trying to do it live streaming, it's a little bit more difficult, yeah? But really what I'm trying to get across here is this is just a process, yeah? And that particular process, it's just there's just a lot of hard work to it, yeah? You can see that in SPSS when we put the values in, we could build the model really quickly, and it did agree with what we actually estimated by hand. Okay, is everything okay? Okay, I just want to talk about just something else, yeah, which is just one final thing, yeah. Before then we can start we can let it go. Is goodness of fit, yeah. So like in a moment ago in SPSS, I'm just going to unshare the desktop now, yeah. So I'm not sharing anymore. Okay? So you see in SPSS I had that R squared value. So what the hell is that R squared value? So I'm going back to YouTube now, guys. Yeah. So I'm going back to YouTube, and I suppose the question now I have is a goodness of fit question, which is the R squared, and how the hell do we calculate that particular R squared? I mean, how do we do that? Yeah. So I just want to just do. Are you all back over here now? Okay, brilliant. Okay, so everybody's. I'm back on YouTube now. Yeah. So let's just draw this again. Okay, so we have our independent variables here. We have our dependent variable here. And let me just do my line of best fit. Okay, so I'll just do my line of best fit here. And let me just do some observations around that. So here's our observations. Okay. And I'm just going to concentrate on one observation. Yeah. So this is our y, and this is our x's. Yeah, along here somewhere. Yeah. Okay. So I'm just going to concentrate on this particular observation. Yeah. So don't forget, what we're trying to understand is we're trying to understand the variation in the dependent variable. And how the hell do we calculate variation? Well, we get the average of the y's and we get the sums of squares. Yeah. So from a y perspective, when we look in this direction, okay. So here's my I here. Okay. I'm looking in this direction here. Okay. I could look at all of these particular values. Okay. These observations. Yep. Okay, I'll just mute that there. Okay. And we could calculate the variance of them. Yeah, so we could have the variance or the standard deviation. But effectively, we would have a mean value. Okay, so let's just say, just so that this works here, I'm just going to put the mean of the y's along here. So there you go. There's my y bar. Okay. Now, what we have here is this: is that excuse me, okay, is that we have an amount of variation that we're trying to understand. Yeah. Okay. So we have an amount of variation that we're trying to understand. Uh, Effectively, let me just get up. I have something similar here. Yeah. So it's let me not use that point. Okay. Just maybe just ignore this here for a moment. Yeah. Okay. Let me just do a different chart, because otherwise I'm going to have some negative values in here when I draw these things out. Let me just do this again with a chart that probably works a little bit better. Okay. So here's my x's, and here's my y's. So this is my dependent variable and my independent variable. And let me just do a line here. Okay, this is my regression line. Okay, this is my y hat line. Okay, so it's the regression. Yeah? It's equal to some b0 plus some b1 times x1 plus so many different independent variables maybe in the mix. Yeah. But effectively, what we have is we have observations, and let me just say that the y values we have, when we take all the y values, we could calculate a y bar. Yeah. Okay. And let's just choose an observation. Let's say the observation is here. Okay. So when we calculate the variance associated, with the y variable, effectively what we do is we calculate how far the distance, yeah, okay, that this y value is away, okay. This y value, this is an observation, yeah. The distance that this y value is away from the mean value, yeah. Not right, because we calculate a y minus y bar. Actually, we square them and we get the sum of them. So we calculate sums of squares, yeah. Okay? So this is sums of squares, yeah, that we calculate, and we actually get the average of them, which gives us the variation. Okay? But if you look at two things here, yeah, is that this particular variation, yeah, let's call this the total sum of squares. So this red line here, so from here all the way down, we could call the total sum of squares. Yeah, if we did that for all of the points, we'd have the total sum of squares, which is effectively this thing here. Yeah. Okay. Now you can see that the blue line actually splits this red line here up into two portions. Yeah. Okay. So it splits it up into this section here and this section above it. Yeah. So this section here, the lower section, yeah, is basically what the model is explaining. Yeah. So this is the explained sum of squares here we could calculate. And this piece up here, okay, is the see, the model is underestimating this particular point. Yeah. So this distance here we call the residual. So this is called the residual sum of squares. Okay. But my point being this is that the total sum of squares in the dependent variable can be broken up into two different portions or two different types of sums of squares. The estimated sums of squares that the model gives us, and also the residual sum of squares. So effectively now what we have is we have that the total sum of squares is equal to the estimated sum of squares plus the residual sum of squares. Yeah. Now, I just want to have a look at this in a little bit more detail. Yeah. So let's just divide across by TSS. Yeah. Okay. So if I divide here by TSS, I end up with 1. So 1 must be equal to ESS all over TSS plus RSS all over TSS. Don't forget, these two things here are just ratios. Yeah. Okay. This here, okay, this thing here, yeah, okay, is effectively it's effectively how much, it's the proportion, yeah, okay, of total sum of squares, yeah, that's accounted for, yeah, by the estimated sum of squares. That's what this bit here tells us, yeah, okay. So this tells us what the model, so it's the proportion, okay, of total sum of squares, yeah, accounted for, okay, by the estimated sum of squares. So this is really important for us, yeah. Where this bit here tells us, the proportion of residual, yeah. Okay, so it's the proportion of the total sum of squares accounted for, okay, by the residual sum of squares. Okay, it's the error in the model, yeah, relative to the total amount that we're trying to estimate. Right? So if we want to figure out a goodness of fit, yeah, okay, well, if we want to know the proportion, yeah, okay, how well the model actually fits this estimate, how well it actually fits the data set, we're really interested in this thing here, and we can calculate it. It's basically 1 minus the residual sum of squares over the total sum of squares, because when we bring this over, it becomes negative, is equal to ESS over TSS. Okay. So we can actually do that calculation pretty easy. And this thing here, okay, we call this thing here R squared, yeah. This is the proportion, yeah, of the variation in the dependent variable that's accounted for by the variation in the independent in the independent variables. Yeah. Okay? So what the hell are these? Well, let's look at them mathematically. So the total sum of squares is pretty straightforward. Yeah. The total sum of squares, and don't forget it's in the dependent variable that we're talking about. Okay. Well, the total sum of squares is equal to all of the distance that each y observation is away from the average of the y's, okay, squared, and it's the sum of them. That's the total sum of squares. The estimated sum of squares, estimated okay, sum of squares, okay, let's say ESS. Well, that's the distance between the estimated values, okay, and the y bar values. Yeah, okay. So it's how good the model actually is itself. Yeah, okay. Squared. Yeah, it's estimate, the distance between the estimates and the y bars. Yeah, okay. And it's the sum of those, and then the residual sum of squares. Okay. Well, it's this piece here, okay? So it's the distance between the y values and the estimated values. So the residual sum of squares is equal to the sum of the distance between the y values and the estimated values. So now we can actually have r squared. So now we end up with r squared is simply equal to 1 minus the residual sum of squares, we said, or SS over the total sum of squares, which gives us r squared as 1 minus the sum of the y's minus the y hats, yeah, which are the estimated values, divided by the total sum of squares, which is the sum of the y's minus the y bars, yeah, squared. So actually we could calculate that r squared value ourselves by just calculating these things here, okay, with respect to the table that we had earlier on. Yeah, we know the y values, we know the y bar values, so we can actually calculate y's minus y bars. We know the model, we built the model, so we could fill in into the model all the x1s and the x2s, and we could get their estimated values, and we could take them away from the y's. So it's actually straightforward to calculate that r squared. This r squared here is known as the coefficient of determination. Okay? If we multiply that by 100, it gives us a percentage, yeah, and it's the percentage, okay, of variation in the dependent variable accounted for, okay, by the variation in the independent variables, right? Effectively, that's basically what that coefficient of determination is. And then we could calculate the coefficient of indetermination, okay, which is in relation to, well, I suppose it's 1 minus r squared, isn't that right? Okay, that's what we would have. It's the other piece that we haven't accounted for. But let's not talk any further about that. Okay, guys. Hopefully that this was in some way helpful for you. Yeah. As I did say earlier on, your assessments, yeah, are coming up. We'll release them. We're going to release the assessments on Monday morning. Yeah. Okay. So hopefully then you'll have a little bit of a better understanding of actually what's going to be expected. As I said, it's just an exam paper. Yeah, it's a past exam. We've taken a lot of exam papers, past questions. We've brought them together. Everybody's going to get an individual one, and you'll have a day to answer the questions and to submit them in. Okay. How long are we here? It took an hour and 10 minutes. That is, so a lot of work there. Yeah. I'd be happy enough there to leave it there, guys. To be honest with you, yeah. I'm just going to go back to you now on Teams, yeah, and just maybe see how you are getting on. Yeah, is there any other questions? Are you okay? Hi, Connor. static coming there through there, Connor. I don't know whether you have a question. Have you got a question? Yeah, I can hear you. Yeah, brilliant. Yeah. Nina. Yeah, that's what I'm going to do. I'm going to upload that video on YouTube. I will do that. Yes. Yeah. It's recorded on YouTube, and when I stop this, YouTube will do their process. I think it takes about an hour for it to release it, and then it gets released. So it will be released on YouTube for you. Yeah. Okay. I'll send you the link in Teams. Can we use Teams? Yeah. If we have any questions, if that makes sense, in the sense that in relation to the assessment, if anybody has any specific questions and they want to have a conversation, we can actually I can take a call, which is if you want me to try to let's say demystify any of the questions that might come up on the assessment that we're going to do this next week. Yeah. Okay. You're getting a sample paper next week, and then I think okay. Okay, my guys, you just have a good evening and take care. Yeah, obviously things are a little bit crazy out there. Yeah, just keep yourself safe. Yeah.